All right. Um, so just testing my microphone to make sure you guys can hear it fine. Nice. Okay, thank you so much for coming today. It's a nice day. I hope you are enjoying it. We're going to talk about the acoustics, and normally questions in acoustics are very simple, very easy. You just need to plug in the numbers, nothing fancy about them, and then you're good to go. We'll solve the examples, and then I will show you Excel files on how like the assignment is done and things that you need to do. So there will be some slides that I'll tell you, I'll show it to you later on in the Excel. But essentially, starting with, sorry, I'm struggling here a little bit with there you go. So essentially, anything that applies to wave applies in the acoustics as well, from frequency and the concept of lower pitch and higher pitch in the periods and how they are different. So all those apply to sounds when we're solving these questions. The second thing to remember, just as a quick refresh for your memory, is you have all these things happening. Anything beyond that is pain, and where we talk is normally around here, right? It's vocal range. Those you definitely know from your slides as well. But now here comes the first equation that we deal with. This is the concept of sound pressure level. You're going to see sound pressure level a lot in your assignment and in the questions that you're going to solve, but this is the basis for it, right? That's the equation. You have the P reference, which is this number, and you have P from here. It's rarely given as a question for you to solve, right? It's just for understanding the basis of SPL or sound pressure levels. But if you're given to solve it, it's very basic, right? You just plug in the numbers and you're good to go. We have these questions, which are called essentially when you have multiple sound pressure level or sources, you want to solve and find out what is the final answer for adding all those three together, right? So there's two solutions. There's method 1 and method 2. And when you want to solve these, method 1 is normally the easiest. You don't need any calculators or anything. When you have these three sound pressure levels or noises or sources, there's a rule of thumb table, which is here. Essentially, there is an option here, that like the first column guides you through what you need to look for and then the action that you need to take, right? It says when two decibel values differ by 0 or 1, what's the action? Add the following amount to the higher value, and the higher value for us, in this case, when we're comparing 30 to 52, is 52, right? So the difference is not 0 to 1, it's not 2 or 3, it's not 4 or 9, it's 10 decibels or more, right? The difference is about 22. The action you need to take is adding 0 decibel to the higher amount, which is this 52. So we keep 52. Now that we have 52, didn't add anything, comparing 52 with 50. You move on, 2 by 2, right? So 52 to 50, the difference is 2 decibels. The action, adding 2 decibels to the higher value. Sorry. The action is adding 2 decibels. Too many colors. Sorry, second. There you go. 2 decibels to the higher value, which is the 52 again. And then the answer is 54. Does that make sense? Does it matter in which, do we need to sort the numbers or not? It really doesn't matter. You can do it any way you want. If you compare 30 to 50, the difference is 50. You keep the bigger number. You do not add any decibels because it's more than 10. And then you compare 50 to 52. The 52 is higher number. The difference is 2 decibels, and you add the 2 decibels. So really, the order doesn't matter how you compare them. Any questions? Now, that's the simplest method if you have it on the exam, but you have the method 2 as well, which is using this equation. All you need to do is to write down this 10 log and then sum all those SPLs that you had in the previous section. You definitely need a calculator for this one, but once you do it, you'll get the final answer. As you can see, the difference is only 0.14. So pretty accurate. Now, can we add things linearly? No, because everything in essentially acoustics is logarithmic, right? So when you're calculating the average, you cannot do that. Questions? We have this table. It's perceived change in SPLs. And it's called Human's approximate doubling or halving of sound loudness by an increase or decrease of a bell or decibel. And then in the table, you see a subjective change and an objective change. When we say subjective, it means that I ask you a question and you're like, how loud is the SPL now? Or how loud is the source? And you say, I hear it much louder or twice as loud. That's how you describe it, right? According to this table, I will interpret your answer, which is subjective, to this objective value, more than 10 decibels. Twice as loud, plus 10. Louder, plus 5. Just perceptibly louder, plus 3. And then it goes the other way with negatives too. Does that make sense? Now, one last thing to remember from this table is that there is one item on the left side that can be mathematically represented. Which one is that? Knock on the table for Daniel. There you go, guys. Knock on the table, do not forget. She said twice as loud. Why is that? Because twice as loud can be mathematically presented as 2x. Same with half as loud. I remember some people were struggling with that on exam. If I don't know if the exam is going to be like including same questions or not. I have no idea. I mean, the same concepts, not the questions, but this was something that some people were struggling. So if in the question you see something that says it's now 2x or divided by 2, that's referring to this table. Some people didn't remember what it is referring to, like how should they understand what's the changes in decibel? So that is the difference, right? Now, you can other ones like work too? Yeah, like much louder. You know, remember it's plus 10 decibels, but like I'm just saying that if it's in mathematical order rather than subjective, remember that it's from this table. Any questions? Okay. The next type of questions are these, and this is about SPL and the distance. You're always given a SPL1, a SPL2, R1, which is distance, and R2. And for solving any of these questions, you're always given 3, and 1 is the one that you're looking for. So you might be given SPL1 and SPL2 and look for R1, but given R2, you just need to plug in the numbers and find the final value. It's as basic as that. Like nothing fancy. You probably need a calculator when you're dealing with logs, but just to remember. Any questions? Okay. Now we have something known as reverberation time. Oh, sorry. The reverberation time is also very straightforward. We are also going to see how it's done for the assignment. But essentially, you have TR, which is the reverberation time. You have the room volume, and then you have this entire 6AS. The only important thing for all these questions is this. The AS is the total absorption of surface area in a space. And how that's calculated is using this. What happens is you multiply the alpha of that surface by the surface area, right? And what does that mean? That means if you have a room like this, which mostly is white wall on one side, then you have the screen, then you have a poster, then you have windows, you need to calculate them individually for each one. So this will be the alpha of the door multiplied by the surface area of the door because it's on the wall, right? Plus the alpha of that poster, whatever that alpha is going to be for that, multiplied by the surface area, plus the wall coefficient for the wall, plus the surface area of the wall, and so on. The question of how detailed should it be? Should you consider the, for example, the posters on the wall? Should you consider things that are blocking the wall, like that container? It's really an engineering question and up to you. It's where you state your assumptions and you say, I did this because of this. Now, the only important thing to remember and is normally confused is that the alpha or the absorption coefficient of the surface for open window is 1. And 0 for hard, smooth surfaces known as acoustic mirrors. And essentially, when you have the window and it is 1, nothing is reflected, right? The sound just goes through. Any questions on this? Yes.
Can we use 0.161 instead of 6 AS? Because I used it, we had it in the lecture notes, so I use 0.161 instead.
0.1?
0.161.
Instead of 1 divided by 6, it was 0.161 in the lecture notes.
Oh, yeah, it doesn't matter. Yeah.
It changes like a little bit. Instead of 166, it's 161. But final result shouldn't change that much.
So you're saying that instead of 1 divided by 6, it's a value that is multiplied, like 0.1 whatever, 161?
Multiplied by 3.
Yeah, you can do it both ways, doesn't matter. Right. So no questions so far? So if you don't have any questions, you have a few minutes to solve this question on the board. The answer is at the bottom. So the first one is going to be a practice. Try not to look at it. And then once you do that, try to solve for the other two, the 0.3 and the 0.9. You are calculating the reverberation time for this room.
Cubic
Yep.
meter, right?
Yep.
Instead of square.
Yep, sorry. This cubic meter, this should be cubic meter, not 0.2. So that's a
Make two scenarios, one with the carpet and one with acoustic pen.
Yeah,
or
exact-
them together.
no, two separate ones. So calculate once the floor is covered with this and once with acoustic panels. This is for walls. Do we have answers? Does anyone have locksmithers for me? Yeah. All right, do we have answers? Okay, what are your numbers?
If we use 0.161, the formula that we have in the lecture, it's 0.425 seconds.
So
But
it's
if I use,
too many numbers to remember. Can you just
Sorry?
go one decimal?
0.425 seconds.
0.4, okay.
And if I use the other formula, the one that he gave us, it would be 440, 0.44.
For the formula, it doesn't matter. It's just the alpha. What happens when you change the alpha?
It changes the absorptive.
Yeah, and what was the numbers? For that one, did you come up with the same number?
No, that's what I'm saying. You get slightly different numbers
Like you get
depending on the formula.
0.4?
0.44 or 0.42.
Really?
It's because
For
one
this one.
divided by 6.
For the like
first
the
one,
regular? Yeah, what did you get for the regular one?
same.
The same number, but the difference is like in like maybe like 0.56 instead of 0.557, right?
It's 578.
Yeah, so it doesn't matter. So you got 0.57 for this, right? And what did you get for this one?
0.4.
0.4. And how about this one? Is that 0.3 for this one, right? So that is correct. So you can see. What numbers did you get? What were your numbers?
For both.
When you apply both? Okay. And Kirash, how are you at the end? Sorry, putting you under spotlight. Others? Between? Are playing games on computers? No, honestly, did you calculate it or not? Doesn't really matter if you did it. Okay.
0.3 and that's 0.34.
For these two?
For the carpeting one,
Yeah.
I think I missed it.
Okay. But did everybody calculate this one correctly? Sorry, what was the question? So you need to divide the 600 volume, which is given, divided by 6, multiplied by this entire, sum of this entire thing, which is 173. When you sum these three, it's going to be 173 because it's area multiplied by the alpha. And when you sum that, you have this final number. You divide 600 by that number multiplied by that 6 or multiplied by 0.16, whatever is easier. And you get that number. Does it make sense? All right. So the overall idea, all this example to say this thing. This equation is your volume divided by area multiplied by the alphas, right? As you increase the alpha, you increase this entire A, right? And the reverberation time goes down. That's the whole concept. Now, the idea, do we need a lower reverberation time or do we need a higher reverberation time? That's up to you and what you're doing and where. Is it a theater or is it a classroom? Is it an amphitheater or is it your home? Right? That reverberation time matters there. So there is no correct answer whether to increase it or decrease it. It's really up to the ranges provided in the guidelines. Does it make sense? All right. The next option we have, this is kind of important for your assignment. It's called the concept of transmission loss. This is the equation. And essentially, you can solve it either for tau or you can solve it for transmission loss, depending on what you have. If you look at the first one, it's an all brick wall. And essentially, it's not a composite TL, but it's a transmission loss for that one because it's just one single surface. And you can see that the transmission loss for this surface is 50. So you only get 50 decibels out of the 100 that you received. Does it make sense? Now, if we add a tiny window, you can see that this number drops significantly. It goes to, it's 11 less compared to what you had when it was the whole wall. So you get 71 out of it. As you see this window increases, it's 74, 77, and 80. You can see the difference between these, right? One single window is enough to just change everything. And then as you increase that, the difference between this single window and this one is only 20. So that's why about 20, it's not exactly 20. Sorry, it's about 9, right? That's why it matters. A tiny window can change everything. And compare that transmission loss to this. Does that make sense? All right. Now, what is the overall concept here is that you get all the surface areas. You need to sum all the type of surfaces that you have divided by the tau multiplied by that surface area. So this is for transmission loss, and this is for composite transmission loss. Does that make sense? Because this one is a single surface, and this one is multiple. So when this is two different types, you need to multiply the surface areas by their taus. Any questions? This is the basic concept. I'm going to show you in the Excel file what it means for the assignment later on, like where you incorporate the equation. But any questions on the concept itself? No? All right. there's something wrong with my scroller. The next idea is noise reduction, or NR, and you got SPL1 and SPL2, and it's a simple subtraction. But normally it's not that simple because you have to essentially expand this to this. And this is normally given to you. So you get that entire equation, the answer for that entire part of the thing. It's normally given. If not, you can calculate it, but normally given. And then you have the S. This S is only the dividing wall. Remember that. So if you see something like this on the exam, you don't need the entire room area. You just need the dividing wall. Right? So you have the SPL1, a drop, and SPL2. This wall is dividing them, and you need the absorption in the receiving room. And you just plug in all the numbers, and you'll be able to calculate it. Right. This is the basic guidelines for the questions in your assignment. Calculate your 12 values from given TL values using that equation. Consider all paths the sound can take. Apply the composite TL formula, and then the indoor SPL using NR formula. And then we're going to solve an Excel sample for it, which is your assignment. But I'm going to show that to you later. Just a quick pause. We need to look at the STC for a second. So we're going to solve a STC question. I'm pretty sure you covered STCs in the classroom, but to just do a quick review, sound transmission loss is a rating system for indicating a surface ability to block the sound in those certain frequencies. So it's a rating system, right? And if something is rated as STC 25, it means that normal speech can be easily heard. If you go to, I don't know, a hotel that is not good for acoustics, you can hear your neighbor next door, what they're talking about. We all have that experience, right? Then at 40, if something is STC 40, you will have some sort of privacy. And then here is something very interesting. At 50, the very loud sounds are almost blocked. And it can go all the way up. Now, how is this rating awarded to a product? To award something to a product, to award a point to the product, you need to have two things. Number one, you have this STC curve, which is the reference curve. This curve essentially indicates if a product needs to receive this rating, it needs to be matching kind of with this STC curve, right? Now, the idea of a product matching exactly to this STC 25 curve is a little bit not possible, right? As everything else, a lot of things can go wrong. So you get a product profile. This is the product profile for the STC, right? To award this, you need to have check for two things. Number one, no single frequency. These are the frequencies, right? No single frequency band may have more than 8 deficiencies, meaning that this entire thing should not be more than 8. It's 5 now. Now, I want you to pay attention to this one. This one is not a deficiency because it is essentially performing better than the curve. When it means it's performing better than the curve, it means that it's actually better. It might get STC 26, right? The second option is that the total of these deficiencies shall not exceed 32. What does that mean? It means that if you sum all these deficiencies that we have here, they cannot be more than 32. Does it make sense? Okay. Any question on this so far? Now let's check this example quickly. This is the SDC curve that we have. And this is your curve for the product. When we calculate this in Excel, you can see that the test, you have the test SDC, SDC contour, and everything else. But no single deficiency is more than 8. Right? So nothing is more than 8. So number 1, bullet point, passed. Number 2, it's exactly 32. So it should be more than 32. So this one receives the SDC of 25. Does it make sense? Now let's see some SDC action. Right. This is my SDC. And normally you're given the SDC contour, transmission loss, and everything else. Then you have a test SDC, which is essentially this number. And then you have the SDC curve. How's that calculated from SDC contour to the test SDC? And then the deficiencies is calculated using this simple equation. E2 minus B2. This second part of this is an if clause. You can either use an if clause in Excel, or you can just multiply it if E2 is more than B2. So what it says is that subtract this and multiply it, but that multiply means that apply this only if this is more than this. So it's not an actual multiplying the numbers, it's a conditional formatting. So you can use an if clause if you want, right? Now, we're doing STC 25. You can see nothing is more than 8, and this is exactly 32. Now, you might be like, Farzan, why can't we do 26? Let's give it a try. 26, nothing is more than 8, but the total is more than 32. Let's do 40. You can see now everything is red almost, except the first one. Everything is more than 8. And this one is more than 32. What if we do 72? There you go. Now everything is red, 760. Right. What if we do 25? But everything goes well. What if we do 24? So why everything still passes, right? Why should this be STC 25 instead of STC 24? Sorry, Dan, can I say it again?
Because it also passes 25.
And knock on the table. There you go. Because it also passes 25. Or put it in another way. When you are a certifier and your manufacturer comes to you, you're going to send that guy out of the door very pissed off if you give them a lower rating. So they always try to get the highest one, and you as a certifier, you try to give them the highest thing that they qualify for. And in this case, they qualify for 25. Does it make sense why we do it on 25? So you need to always do the testing in future or in reality, or even just for if you're solving it for some sort of question, try to reach the highest always.
Use increments of 1 decibel, or can we use like half decibel?
Like 32.1? No, that's how you do it. You gotta stick to the no decimal numbers. Yeah. Yeah, no decimals. Because 1 decimal means 1.1, right?
No, I meant decibel.
Oh, decibel. Yeah. Sorry. So you were saying decimals. I'm so sorry. My hearing problem. Yeah, always you do that with 1 decibel. Yeah. Okay. Any other questions? All right, I'm going to stop sharing on Zoom for a second. And we're going to solve the assignment on the Excel. So I'm not going to record that one, and please don't take photos of that one because you're supposed to solve it yourself. But I'm going to show you how it's done. And let me just end this